solve the problem directly. We'll do assignment 7, and that will give you a lot of clarity about what we have learned so much about availability. Okay. So I will not send you. I may not be able to send you the written solution. So probably recording will work for you. For one problem, I have written it in the handwritten that I'll send you. I don't know for all I can send you to. Okay, so assignment 7, problem number 2. If you can refer, if you can open it. I have written, so I will read it from there. Assignment 7. Since I have put it somewhere, no problem. I got it. Oh, no. I got the I got the assignment. Yes. Great. So if you see assignment 7, question 1 is already done. Okay. That extra-G distort is not as generation that we have seen in the last class. So we are going to solve assignment 7, problem 2. Okay. So there is a piece of metal. There is a metal block. And metal block is cooling down. And temperature of metal block is going from, let's say, T1 metal to T2 metal. Temperature is decreasing from 200 degrees Celsius to 100 degrees Celsius. Okay. Whatever heat you are removing from this, that Q you are feeding to an engine. This engine may be reversible, irreversible. So that will be described in the problem. So right now for till part C, engine is reversible heat engine. So since you are feeding that heat ejected by metal block to engine, it will do some work, which is useful work. Okay. And then some heat will be rejected where? To environment. Environment is a reservoir. Environment. P naught, T naught. Fine. So this is QR, Q rejected. Perfect. So in part A, it has been asked that heat removed from the metal, which is very easy. We have done it last time, I guess. So this C into dt. So Q you can say C into delta T, which is T1 minus T2. If we want to know the value, this comes out to be 40 kilojoule per kg. Everything in per kg. Okay, you can check. Fine. So the first problem is that heat. Okay, so that's now A is done. Part B says change in availability of the metal. Okay, or what we call non-flow exergy of the metal. Since it's per unit mass, it's availability. So basically, what we need to calculate is d phi for metal. D phi for metal. Okay, and you know that this is going to be d of u plus surrounding P naught V minus surrounding T naught S, which is nothing but U2 minus U1 plus P naught V2 minus V1 minus T naught S2 minus S1. Now let's talk about U2 minus U1. Since I told you that metal block will cool down slowly in a reversible manner, we know it. Or if not, If you are not convinced, then I'll write the assumption that okay, I am assuming it will cool down reversibly. Otherwise, you cannot solve it. Then we need extra information if it's irreversible. So let's assume it's cooled down irreversibly. Okay, and there is no expansion in the metal. So dV is 0. The moment you say dV is 0, we know that work done is 0 by the metal. So if you apply first law on metal, dou Q is equal to du plus delta W. This term is 0. Okay. So this is U2 minus U1. And you are writing it for metal. For metal, you have to maintain the sign also. Metal is rejecting heat, so minus 40. So U2 minus U1 is going to be minus 40. Then you know P naught and you know V2 minus V1. Oh, there is no V2 minus V1, sorry, because it's a metal, it's gone. Now we need to calculate, sorry, so there is a minus sign, so this is gone. Minus T naught S2 minus S1. Who will tell S2 minus S1? So again, it's a reversible cooling. So S2 minus S1 we can calculate from this heat is reversible heat from metal side. Okay, from metal side, remember, reversible from metal side. So S2 minus S1 you can write dou Q rejected by T. Is it fine? Can we write it? Any comment? Which T? Or there is something missing, you think? Anyone? I want S2 minus S1 for metal.
Sir, T is variable, so I guess we have to write ds equal to.
Yes, very good. Basically, you are saying you have to do this way. Of course, dQ is reversible, but temperature of metal is still changing, right? And dQ reversible is, we know, C dt by T. T goes from T1 to T2. So S2 minus S1 metal will come out to be C ln T2 by T1. Put the values in Kelvin. Okay. If we put values in Kelvin and everything, since of course T2 is less than T1 because it's cooling down, it's suppose that entropy come out to be negative. It's come out to be minus 0.0949. For D5 will 40. So minus 40 minus, there is a T naught here, 300 into minus of 0.0949. If we do that, we'll find D5 is minus 11.51 kilojoule per kg for metal. What does it mean? Availability of metal has decreased, of course, because it is rejecting heat. So basically it is losing the available form in terms of heat. So its availability has decreased by this much. That's why D5, which is final minus initial, is negative. That is point B. Answer of B. Then C part. Now what you are doing, you are feeding this to engine. Okay. To engine. Okay. Which is reversible. In first case, it is written that useful work output if engine is reversible. Okay. See environment. So if you so W max useful, so the useful work which you can extract from engine is going to be simply Q minus Q1. Okay, no doubt about this. Right? Okay. Now, what we said that metal block is cooling reversibly. That already we assume. Huh? And engine is also reversible. Okay. And environment is also a reservoir. Fine. In order to do that, what we have to maintain? Can anyone comment? If we are saying everything is reversible, Can you say anything about the engine temperature? Anyone? That what will be the temperature? This point temperature where heat is coming in, this should be always equal to the temperature of the metal, whatever instantaneous temperature of metal has. That is hidden there in this question. Then all everything will work reversibly. And then only you can use the maximum useful work, or what you call reversible work from the engine. Okay. And then same thing is true here also. This needs to be maintained at T naught, which is environmental temperature. That's why we know we say this concept of boundary temperature or local temperature at the boundary. Then only this heat transfer will be reversible. Okay, that is one thing. Fine. Now, what we know that if everything is reversible, then delta S universe should be 0 or SG should be 0. When you say delta S universe, we have delta S metal block plus delta S environment or heat the reservoir, so plus delta S engine is equal to 0. Can you even tell what is delta S for engine? Yes. What is delta S for engine?
Sir,
Yes.
it's
Engine.
a cyclic
We are talking about
process.
cyclic device. Remember, delta S engine is
0.
0. It's a cyclic device. Let's talk about delta S metal. We have just seen C ln T2 by T1. We know the value. We have to talk about delta S environment is equal to 0. We know that environment is, so this is QR, right? And we know that environment is a thermal reservoir and heat is getting rejected also reversibly. So we know C ln T2 by T1 plus this I can write Q rejected, and since this we are giving to environment, positive sign QR divided by temperature of environment is equal to 0. So this way you can calculate QR, which comes out to be T naught minus sin C ln T2 by T1. So if you take minus inside, it will T naught C ln T1 by T2. So QR comes out to be 28.49 kilojoule per kg. Once you know Q and QR, it's very easy. You can calculate W max useful when engine is working reversibly. It's simply 40, the heat given to the engine minus heat rejected, which is 28.49, so 11.51 kilojoule per kg. What you observe here, whatever exergy you have supplied to engine, this much. Remember the answer of part B, exergy change in metal. So whatever exergy you have extracted from metal and given to the engine, and since the engine is working reversibly, there is no wastage of exergy. Everything is you are getting as work. So this is the maximum work which you can obtain. So note down. I mean, just take a pause and think that whatever exergy you supplied to engine by decreasing the exergy of metal, everything you can convert into work if your engine is working reversibly. Great. Let's talk about part B. Okay. In part D, what is part D? Thermodynamic lost work. I told you lost work is nothing but exergy destroyed, because you can't, you destroyed it, and that we know T naught SG. Okay, but exergy will be only destroyed if engine is working. Engine is working irreversibly. Otherwise, you see, you have seen if engine is working reversibly, everything will be converted into work. So, of course, and that is given in problem also. It's a irreversible engine. So output is not going to be 11.51. It's going to be less irreversible engine. That's why we have lost work. And it is given that the work output of engine W is 10 kilojoule per kg. Okay, great. So basically you are giving some Q, is of course 40, but this time work is not 11.51, this is 10 only. And some heat is going to rejected, which is basically 30. Okay, heat engine, irreversible, metal, environment, T0. Okay. So basically for lost work, you have to calculate S generation. Okay. And the moment you say S generation, you know that S generation is delta S metal plus delta S surrounding plus delta S heat engine, but heat engine is again a cyclic device. So that will be 0. So the SG will be only delta S metal plus delta S surrounding. Okay. Delta S metal is going to be same. It's not going to change. CLN T2 by T1. Now we have to think about delta S surrounding. Okay. That is very easy because since we know that heat transfer is happening what we call as reversibly to the environment. Okay. So since heat transfer is reversibly, we can always calculate delta S surrounding as simply heat given to surrounding is 30 by T0. So Sg, if you put these values, Sg is coming out to be well, I have not calculated Sg directly. I have put it in this form, and then I have multiplied with T0. Okay. Can anyone tell how much it will come out? Can you guess? If you put value of everything T0 and Sg, whatever you're calculating.
1.5.
Yeah, very good. Because you are losing this. What kind of irreversibility is internal or external?
Internal.
Internal. We said engine is working irreversibly. Somehow due to friction or something, engine is losing something. So internal irreversibility. And due to this internal reversibility, your lost work is this much. So basically, apart whatever exergy you are taking from metal, that is 11.51, this much is getting destroyed due to irreversibility of engine, and you are only getting 10. Okay. Same problem. So we have solved it this way. Same problem. Let's solve it from exergy balance. We have done exergy balance also, and ultimately these all are same. Either you calculate SG or exergy. I have told you that this is just like you know you are going to the same destination through different paths, or we are saying the same thing. So let's see whether exergy balance works or not. Okay, so let's try other way. Yeah. So same problem, 2 from exergy balance approach. Okay. If you remember, if not, then you can refer the lecture. X2 minus X1 system, that is delta X, is equal to X due to heat to system, X due to work by system. This system will lose, minus X destroyed. Can we do it through this? If we can find part D, X destroyed through this path. Okay, let's see. Since it's everything in per kg, you can say it's a 5 2 minus 5. Doesn't matter. Okay, so both are same. Okay, this we have calculated already, if you remember. Or no, wait, this we have not calculated. Wait, Now let's see for this equation what we need to know. First of all, can anyone comment? System. First we have to share about system. What do you suggest? What we should take as system? We are talking about engine. So what we should take as system? Yes. Engine. What is x2 minus x1 system for engine? Anyone? Let's see. Yes. x2 minus x1 for engine. Who will answer? No guess? Vilas, what do you think?
Sir, x2 minus x1 system.
Engine is our system. I am giving hint. Engine is a cyclic device.
Yes, sir.
0. Okay.
Okay. Yes, sir. 0. Okay, the system is engine.
Depending. So that's why I smartly choosing engine my system. Okay. So it's a cyclic device. So there is no point of confusion. We're always talking about, so this is because engine working in a cyclic manner. So this is 0 for engine cyclic device is equal to x heat to system. If you remember the equation, it's like this: dou q 1 minus T naught by T, where T is temperature of which point? Can anyone tell me? So we are not talking about this X by heat. Can anyone tell me? T temperature of which point?
System.
System, but where? At the boundary, where
Yes,
Q
sir,
is coming to the system, right? That was the confusion. No? When I was teaching exergy, then I took another class and so the point where heat is coming, at that point, it is coming in, not going out. Remember, we are doing exergy balance. So what is coming in is important for us. Of course, what is going out, that will come in a different manner. So this is the dou Q. Okay. And this is the temperature which we are talking about. And here what we assume, so what is exergy? Since Nidhi asked, Nidhi was discussed. What is exergy by the way, definition or availability? Maximum available energy, right? Or maximum energy which can be used as work. You agree, Nidhi?
Yes, sir.
So if you are giving dou Q heat to an engine, okay, at temperature T, where T is the temperature of, let's say, hot reservoir, and T naught is temperature of what?
Environment.
Environment. What is maximum work you can take out? So first of all, engine has to work reversibly, right? It should be a Carnot cycle or reversible cycle, any reversible cycle. Then maximum work which you can extract is eta maximum. And eta maximum is what? 1 minus T naught by T hot, isn't it?
Yes.
Now, if I want this, so I have written TQ 1 minus T naught by TH. Okay, this is first of all any W. This is any efficiency. When this W will be maximum? When process is reversible. So this TH, which you are saying, this metal temperature, this must be equal to T. So basically, that's we discussed before also, that everything is happening reversible. This heat transfer is reversible. So if that is the case, then that is only possible if, so basically when you are saying exergy by heat, the moment you say exergy by heat means maximum energy which is available for work given to system, and that is only possible if you keep the temperature of system equal to reservoir temperature. Okay, let me say, put this way: exergy due to heat, that should be treated as maximum energy available for work, and that will only happen only if T system at local boundary should be equal to T hot. There is no other way. Then only you will say exergy. Otherwise, you cannot say exergy by heat. Exergy is maximum. So in that, with this motivation or with this explanation, by default you have to say In order to calculate exergy, it is whether it's there or not, that's a different thing. But if you are doing exergy balance, then that much exergy will go to the heat engine. So T is nothing but metal temperature. Fine. So if you solve this term, X due to heat, dou Q is nothing but, let's say there is a temperature change by dt. So C dt 1 minus T naught by T. So if you integrate, so it's going from engine temperature. This temperature is going from at this location T1 to T2. So this will be C T2 minus T1 minus C ln T2 by T1. This is exergy due to heat. Okay. Now exergy work by engine is nothing but W. That is the maximum work which you can extract, which you want to know. Okay, which is in case D 10. So engine is we are solving part D, and engine is irreversible. Irreversible engine. So the work which you are extracting from engine is given 10 kilojoule, which is nothing but exergy rejected by the engine by doing some work. Fine. What else we have? And we want to know X destroyed. So if we do the balance, you remember X2 minus X1 system is 0. Okay, that is equal to exergy given by heat, which is coming out to be C T2 minus T1 minus C, or there is T naught also. T naught is missing here. T naught C ln T1 T2 by T1, sorry, T2 by T1 minus X destroyed. So X destroyed will be minus of C. No, simply X will be C T2 minus X will go that side. So C T2 minus T1 minus T naught C ln T2 by T1. This you know is nothing but minus 40, and this you know is nothing but it's come out to be wait.
Sir, will there be a minus 30 for
Wait, first of all, have we done everything correctly that you have to see?
Sir, work by system exergy is left, I guess.
Wait. Well, let me see. There is no mistake first. What you are saying? Come again? Yes.
Sir, minus 10 should also be there, I'm saying, for
Minus 10 should also be there. Yes. Sorry. Very sorry. Yeah. Oh, I forgot it. Na? Yes. Minus 10. Yeah. Minus W. Yeah. So minus 40 minus this term, how much coming? Minus of like 300 into something. Let me check how much comes out to be 28.49. So minus of 28.49. And as someone said that we were, this W is also there if you see the balance. So minus 10 minus X destroyed. If everything is right, answer should match. If not, then there is some problem. Because through this approach, we should get the answer. I have done it from both approach. Let's see whether it matches or not. So this is minus 40. This is fine. T naught CL and T2 by T1. T2 is less than T1. So that's how it should be. Because we calculated in the last part. denote. Yeah, 28.49, and then there is minus 10 also. So it's coming out to be 50 minus 28.49. We don't have this much destruction, no? We have 1.51. So where is the mistake? There is some mistake with sign. Heat work is fine. Work is 10, so it is going out from the system. I think are we making any mistake here? It's given to system. Why it is a minus sign? Probably there is the mistake. Heat given to system. Oh, yes. You see, there is just a mistake of sign here. Go back. So what we should write, dou q? Anyone? It's, see, we are giving it. So sign should be consistent with new. What is dt by the way? So we are giving this to system, right? What is dt? Dt is negative, isn't it? From metal, we know dt is negative because you have to maintain the T of engine also at the same temperature. But heat is what coming to the system, that should be must take a positive sign. So what we should put here? Minus cdt. Okay. So minus, and this will be then plus. Then there should be, yeah, yes. Anyone has any comment? Because see, dt we say final minus initial, but we know that it should be a positive sign because we are giving exergy to the engine, which is our system. Okay. So basically this will be plus 40, and then what else? And then there is no minus, so this is plus sign, and now I will get what I am looking for. That x destroyed will be 40 minus 30, yeah, minus 28.49. It should be 1.51. Yes, that's so. This is minus, this is plus, minus plus. That was a mistake. dt is negative, T2 minus T1. And you are maintaining the local temperature of the boundary also at same temperature. But heat given is positive. So in order to keep dq positive, which you are giving to system, you have to put on minus sign. So what we learned from this example, that even if you do through exergy balance, x destroy is same. So either you go for that entropy calculation approach, entropy generation multiplied by T naught, or through this, answer is going to be same. Okay. Well, I wanted to solve one more problem, but I'm sure you have class. So is it fine if I record it, the second problem, and I'll put it as a recording? Is it okay?
Yes, sir.
Sir, I have a doubt.
Yeah, please. Doubt you should. Yes, please.
Sir, when you solve for part D by
Yeah,
first method, not
first
by
method.
this Excel. Yes,
Yeah,
first method.
yes,
Uh, yes. So
yeah.
in delta S universe, this is C part. I want D
This is
part.
C part. You
D.
want D part. Okay, D part. Yes, here.
So
Yeah.
in this SG part, why the delta S of heat engine is not included? Because it will not be zero because irreversible process.
No. Delta S of
Oh,
heat engine will be zero. It's a cyclic device.
it will be zero. It's a cyclic
Ha,
process. Yes,
ha.
got sir.
But there will be some generation also due to friction and all these things. Okay.
Yes, sir.
Sir, like you told that Gargi ma'am will be taking a test on
Yes.
Friday. Will it be
Yeah.
a objective test or a
I
subjective
will
test?
try to keep, since I am setting the paper, I'll try to keep it objective, and but sometimes putting everything objective is not possible. So maybe a small subjective question also.
Okay, sir. Sir, like will it be on MS Teams or
Yeah, I will share the paper, you solve, and you
okay.
submit your answer. I will not create some, let me see if I can create a Google quiz or something, or you have to write and upload it, whatever it will be. See,
Yes, sir.
one thing I'm telling you, paper will be lengthy, so don't worry at all. We are just checking how much you have. The paper will be lengthy a bit. So if I am giving you 15 minutes, that problem will be, let's say, 20 minutes, so that you don't have time. You just keep on solving. Okay.
Okay, sir.
Yeah. So nothing to worry. And the weightage will be very small. This is just to check that what things you are missing and whether transition is smooth or not. Otherwise, Gargi ma'am will cover few things again probably. That's why. Okay. I'll make sure weightage will be very small. Don't worry. Okay. I'll talk to Professor Gargi. So the syllabus is what we did today: this equation of state and that thermodynamic relation. This availability and all this is not the part of test. That we will cover. So for my class test, there will be two class tests. We'll divide the syllabus half half. This part will exclude. This what we did in equation of state and thermodynamic relation excluded. That will not be there. A thermodynamic relation, let's put it. Otherwise, you will miss the crux. But equation of state will not be there. Half of part and then two tests. That's all. Whenever I write you and then we can fix the time. Don't worry. After a break, because everyone needs a break. Anything, any doubt? Rest two problems I will just record up once you leave the class. If you want, you can stay. So if any doubt, I'll wait for 5 minutes. Otherwise, I'll start recording the remaining part.
Hello, sir.
Yes, please.
Can you go for part
Part
C?
Part C. Which approach? Entropy approach.
Part C, third one.
Sorry.
In the part C.
Which approach? There are two approaches. Exergy approach or entropy approach?
Exergy approach.
Oh, second
Not
approach.
in the part C, in the part C.
Is second approach or first approach?
In the part C, sir, there was only one last one.
Part D we have solved by 2 ways, na?
Sir, I am talking about part C.
Oh, part C. Chalo, yeah, tell me. Yes.
For all reversible engines working between temperatures, efficiency will be same.
Efficiency will be?
Same.
How much efficiency will be?
Efficiency will be off there.
No, your voice is not clear. Be louder.
For all reversible engines working between two same temperatures, efficiency will be same.
Yeah, that reversible engine. Yeah, of course. Yes, yeah. One, what do we call it? This 1 minus T naught by TH. That's what you are saying?
Yes, sir.
Do you know TH this in this problem?
So it is working between 100 and 200.
Who said you? It is working between metal and environment, isn't it? And metal is a hot reservoir, which itself is changing its temperature. So this is not going to work directly. Okay. At every point, efficiency is maximum, and the TH will be the T of the metal, which is equal to the T of the local boundary of the engine where heat temperature is taking place. You got the point? Or not?
I got temperature.
Yeah? Okay, so there is, you cannot, what TH you will take. That is, so basically what we should do, if you want to define eta, where the heat reservoir temperature itself is changing, so this is your metal, so this is your metal. Okay, that's what I was trying to explain this problem, that, and if this is heat engine, if heat is coming here, then this temperature and this temperature should be equal, and metal temperature is decreasing, so this temperature will also decrease. Okay, so if you want to define eta, how we define eta? The eta we define this, let's say small amount of dq, if you give, work done is dw, and this is dou q. Okay, now in fact you can write w by q, which is integral of this. Okay, and then this you can write let's say at that time the local temperature is oh, in fact no, sorry, we can't do anything. There is no overall efficiency. There is efficiency at each point, at each temperature of metal. So efficiency itself is a function of reservoir temperature. Okay. Anything else? Whatever is coming in your mind, ask. Let's see another problem quickly. Who are there? Who want to leave? They can leave. It will be in recording. What I can do? This course is so much, you know, overloaded. We can't. Maybe in future it will be split into two courses, but right now it's one course. So, and I don't want to miss things. At least you should listen the names. That's fine. Okay. Then problem 3, it will be as recording. If you have class, please leave at 2. It's on you, because anyway this recording will be passed to you. Assignment 3rd problem, assignment 7, problem 3. I'll do it very fast using exergy approach. So okay. So you have in this problem a piston cylinder system, and 0.05 kg of steam is trapped in this. Okay, and then what is happening, that it expands. So work is quasi static. You can say there is a spring piston system. It expands against the environment, and it reached to a final state 200 kilopascal, 150 degrees Celsius. So have a so this is stage 1, where you have okay. So this is what is the initial conditions given? Okay. I think in the question I missed the initial condition. Please note it down. The initial condition is 1 megapascal, 300 degrees Celsius. In question it is missing. Initial state, let's say state 1 is 1 megapascal and 300 degrees Celsius. And then when it will expand, it will go to stage 2. Stage 2, where eventually it take a final state of 200 kilopascal and 150 degrees Celsius. Okay, and this system expanding against environment and environment conditions. So environment or surrounding is given. T naught is 25 degrees Celsius and P naught is 100 kilopascal. Okay, so the first problem is asked exergy change of the system. Okay, so x2 minus x1 of the system. So part A is exergy of the steam at initial and final state. And so if you know part A, you know part B also. If you see A, if you calculate x1, exergy at 1, you have to take mass into account. Mass of steam is 0.05 kg, so let's say it m. Okay, and then what you need to know else, u1 minus u naught minus t naught, s1 minus s naught plus p naught, p1 minus v naught. What does it mean by exergy state 1? If your gas will expand against the environment till it attain the environmental state, in that case how much maximum work you can extract, that is x1. Whether it is arriving there or not, that's not a problem in calculating x1. That will be x2 minus x1. If you talk only about x1, then imagine if gas will expand till the point it is in equilibrium with environment, for that case what is maximum work you can extract by the steam, that is x1. Okay, so all you need to know u1, u naught and these properties. Okay, so since temperature is given at state 1 megapascal, 300 degrees Celsius, you can note down these properties by going to steam table. So let's say u1, s1, v1. Okay, u1 how you can know, h1 minus p1 v1. Okay, the pressure is given, and then this state. What is your note state? Means steam properties. Steam properties at environmental condition. Environmental conditions, which is T naught, P naught. Now what you have to approximate here, if you'll see that environmental condition is 25 degree, 100 kilopascal. Okay. Now if you will check the data for, let's say if we'll check steam table, for 100 kilopascal, Tsat is 99.63, whereas our temperature is 25 degree, less than Tsat. So we are approximating it here that whatever property is valid for this Tsat, this saturated liquid, that is not varying much when you go to 25 degree. So what I am saying is U naught, which is U at 25, is roughly equal to U at this Tsat, or basically you are approximating the property with properties of saturated liquid. You will see the PV diagram. You are not on the saturated liquid curve because that temperature is 99.63. You have gone to 25 degree, more lower temperature. So you can be something else, but you are assuming that roughly it is equal to U at 25 degrees Celsius is equal to U at Tsat. Okay. So you know and other things. Just put the value, you will get X1. Okay. So X1 comes out to be, the answer is 35 kilojoule. Okay. Then part B. Okay, in part A itself, X2 also you can calculate because you know all the variables. So it will be M U2 minus U naught minus T naught S2 minus S naught. What it tells you, if your system will expand from state 2 to environmental condition, if, then how much maximum work can be extracted, and this comes out to be 25.4 kilojoule. Okay, so that is part A. Then we have part B. So once you know X1 and X2, part B you can calculate X2 minus X1. Okay, and as you can say that since system is doing work, it's expanding. Okay, what will happen, that is exergy will decrease. So how much exergy will decrease? Delta X will be simply X2 minus X1, which is 25.4 minus 35, it comes out to be minus 9.6 kilojoule. This is part B. Then we go to part C. Okay. In part C, exergy destroyed. Okay. So the moment you say exergy destroyed, all we need to calculate is, all we need to do is exergy balance. Exergy balance. Okay. So exergy balance, if you'll see, this time remember we don't have an engine, and that's why, so X2 minus X1 system, and system is steam. In previous case we have engine which working reversibly, we said X2 minus X1 is 0. But here it's a steam and your process is not cyclic. So X2 minus X1 system is not 0. We have calculated it in part B. It is coming out to be minus 9.6 kilojoule. So that is important to know, whether your device is cyclic or not. If not, delta X is not going to be 0. Here you have a system unidirectional process where a gas is expanding. So it's always hidden that when the moment you take engine, we consider everything for one cycle. Remember, it's not written in the problem, but you consider everything for one cycle. And the moment you say cycle, X2 minus X1 for engine will be 0. Here with steam, it's a unidirectional process. So X2 minus X1 will have some value. Okay. Minus then is equal to X heat to system minus X work by system, which is nothing but maximum useful work by system. Okay, minus X destroyed. Let's go one by one. This we know, minus 9.6. Let's talk about X heat to system. We are not giving any heat to the system. Don't think what is getting rejected. You are only worried about how much exergy is coming to the system. Since we are not supplying any heat to this trapped gas, so there is no point of X heat given by heat to the system. So this is 0. No heat given to system. Okay. Fine. Now you can see clearly that gas temperature is decreasing, steam. So they are going to be change in internal energy also, as well as work also. If both components are there, they are going to be heat rejected also. Okay, there will be some heat rejection. There will be some QR. So if you apply first law on trapped steam, so dou Q equals to du plus delta W. Okay, and since we are so yeah, this is our energy balance, right? So it means that let's say we are going from state 1 to 2, right? We know that steam is going from 1 to 2, so say it W1 to 2 plus m into small u2 minus small u1 is dou Q. Okay, now if is anything given in this problem, so you see that it's written that system is the heat losses from the system is 2 kilojoule. So this dou Q system, if we will write, since it is rejecting heat, it is minus 2. Okay, so you know this dou Q is minus 2, you know u2 and u1, so you can calculate W12. Okay, and W12 coming out to be, if we put value 8.8 kilojoule. Is it equal to X work by system? No. Why? Because see, engine gives you a direct work. That when you draw engine and when you say work output, that is the work apart from this expansion and all this, whatever cycle will do. So that is the pure work. But here it's a unidirectional process. So this W12 is not the exergy. You have to exclude the work done against the environment. So now if you are interested in this term, then you have to say X work by system. That will be W12 minus system is expanding against environment, you note V2 minus V1. Again, we already calculated W12 in the previous slide, because Q rejected was given minus 2, U2 and UN was known. So you know Q rejected, you know delta U. So you know how much is work done. So that was 8.8 minus, if you put the values of P2 and V2 minus V1, this X work is coming out to be 5.3 kilojoule. So this much system energy will go from the steam. It will be converted into work, useful work. Now since we have all the terms, we can apply exergy balance. So X2 minus X1 steam is equal to X heat over 0, because we are not giving any heat to system, minus X work, we know, and we want to know X destroyed. So X2 minus X1 is coming out to be, if you remember, minus 9.6. X work is coming out to be minus 5.3 minus X destroyed. So X destroyed will be 9.6 minus 5.3, I guess. I'll just check the final answer so that there is no mistake. Yes. So it should be 9.6 minus 5.3, which comes out to 4.3, which is correct. Now, if you have any doubt and if you want to check either answer is correct or not, very simple. Calculate SG. Okay. If you want to calculate SG, delta S of steam plus delta S of environment. Right. Delta of steam you can calculate because you know state 1 and state 2. So it's simply M S2 minus S1. And delta S environment is a reservoir. You know how much heat is going to environment. Since you are writing it for environment is taking 2 kilojoule. So it will be plus sign 2 divided by T naught, which is 25 degree, 298 Kelvin. Put the values of S2 and S1 from steam table for steam. put everything, and once you get the SG for X destroyed, you can calculate T naught SG, and you'll find the same answer, 4.3 kilojoule. So ultimately, either you go through exergy approach or entropy approach, answer is going to be same, because it's same thing. The only thing exergy important because here environmental condition becomes important. Against what your system is trying to do something. That something which is against the system, that is becomes important here. So the resistive force which is environment, that matters while calculating exergy or useful work. So with this we completed 2 problems. Third one I will write it and I will send it to you. I think with these 2 problems, this concept of availability and entropy generation is quite clear. If anyone is there, he can ask doubts. Otherwise, I will close this lecture. Okay, Savik, you can leave and stop the recordings. But thanks for your time. Today we
Thank you,
extended
sir.
it. Thanks.
Sir, one question, sir.
Yes, please.
Sir, it means in the next lecture when Gargi ma'am will take, sir, will I
You
also
guys
be
need not
the
to be there. You are free.
Achha.
Okay?
Okay,
You are free. Their TH will be there. I don't know if Gargi ma'am will ask. I'll let you know. If she doesn't ask, you assume you are free. Okay.
Sir, another thing, sir.
Yeah.
Sir, sir, the book you told, no, sir, that
What?
Francis.
Uh,
Yes, sir. Sir, actually, I am not getting that PDF.
no,
Sir,
PDF is not available. I am not getting. I ordered that book online using Amazon. It's coming from US. It's still on the way. It's not available in India. So only 1 or 2 copies. 1 copy is available in the library, which is with me. So it's not available. It's a fantastic book, but it's not there. Okay.
sir, any other means book on means thermodynamics you would recommend means to means
Well, if you are
for
looking
this.
for like scoring, like GATE or any
No,
other
sir,
exam.
not for scoring, sir. Sir, for these type of concepts
Oh no,
means
then I to be very frank, I have gone through many books. I have never seen such kind of book which talks so deeply about fundamentals. You will see, like if you'll see the Sengel book on thermodynamics, you will find it's very good book. Lot of problems he has solved, but that fundamental touch is missing. Why you see now it's okay. It's a collection of information and problems, but again,
yes, sir.
so
Yes.
okay. Once you will be in campus, you can always do a photocopy. Don't worry. I've
Yes,
ordered a
sir.
book. Let's see when I will get it. Okay. Yeah.
Okay, sir. Okay,
Yeah.
sir. Thank you, sir.
Okay, guys. Thank you. Thanks.
Editor, who do you know?